Okay, so we're going to be going to increasingly efficient methods. So the second one is simply a gaseous diffusion separator. Now, it's a very simple process. All I do here is I simply have a membrane in the middle that is dividing a chamber. And on one side, I have a higher pressure. Now, because I have a higher pressure on one side than the other, that will cause the lighter particles to move to the low pressure side. Now, the question you might ask yourself is, well, why do the lighter particles go to one side if there's a higher pressure on the other side? Like, what's causing this differentiation? Well, it's all because of velocity. So the average kinetic energy of the particles are all the same. So the nitrogen and the oxygen both have the same kinetic energy. But what we need to realize is that the nitrogen is faster. Nitrogen has a lower weight. So I could write this way that, let's see here. Yeah, so the mass of N is 28, molecular weight, grams per mole. And the mass of oxygen, O2, is equal to 32. So if it was molecular oxygen, it would be like this, or if it's atomic, it's just 14 and 16. So since nitrogen is lighter than oxygen, it means that if it has the same kinetic energy, well, guess what? It's going to move faster. And the faster the particles move, the more likely it is to make it through that barrier. So the faster particles make it to one side, and the slower particles stay on the other side. You can see here how I can figure out the velocity ratios for my lighter and heavier species. Okay, now let's look at something that's close to real life. So here we have something we'd actually use if we were trying to separate U-235 from U-238. In this case, we have a thin nickel alloy right here. That's my porous membrane. And we have high pressure on one side and low pressure on the other once again. And the U-235 being lighter will go to the low pressure side, just like the nitrogen did. Now, we aren't actually dealing with just pure uranium here. We're actually dealing with uranium hexafluoride because that helps us to turn it into a gas and makes it easier on us to work with. However, we have an issue. Last time we had the difference between 14 and 16, which was still very, very small. But if you're talking about percent difference, when I go to uranium hexafluoride for U-235 versus U-238, well, I've only got a mass of 349 versus 352. This is tiny. It is a very, very small difference. We go from a 10% difference between nitrogen and oxygen to a 1% difference, actually less than 1% difference here. Now, because of this, my amount of separation is going to be very, very small. And so it means that, honestly, this is a huge exaggeration. Like having this much of a difference is not what you're going to see. You'd be seeing, a small amount more of U-235 on the top versus the bottom, but we're exaggerating to be able to show this in a single picture. So how do we deal with this? Well, we deal with it using what's called a cascade. So we have several stages. How many? A lot. To get it to a particular enrichment level. So if I want 90% U-235, well, that's going to take a bunch of stages. If I want 3%, a different amount. But still, I'm going to have to use a bunch of stages to use this process to get where I want to go. So here's a diagram showing how this might work in a cascade. So I am feeding it right here as it's entering. And I have a higher pressure on the bottom than the top. And so you can see that this selected a little bit more U-235. And so after one stage, I go from 0.00725, that's natural uranium, atom percent, to 0.00727. And after another stage to 0.00729. After another stage to 0.00731. Once again, the picture is exaggerated. We don't actually have that ratio. We're just showing how it is getting better and better as we go. And so you can see here that it's only stepping up in very small amounts each time. But eventually, it would get there. Eventually, it would make it to the other, to where I want it to go. Now, all these processes, they're working to change the abundance ratio of the gas. What do I mean by abundance ratio? Well, I'm simply saying, okay, how much of the lighter species do I have compared to the heavier species? How much? And After each stage, this ratio is going to change because I'll have more of the lighter species than I had before. So I could say R prime is equal to alpha right here times my initial abundance ratio. Alpha is the separation factor. That's simply saying how good is my system at separating out the lighter species, in this case U235, than the heavier species. And for a perfect case, it would be equivalent to the ratio of their masses. So the square root of the ratio of their masses. Real life is not perfect though, so it's not going to be that value every single time. And it's usually going to be a little bit lower. How much lower? Not terribly much, as you'll see in an example problem in just a minute, but still a little bit lower. Okay, so we'll stop here for now, but next time we'll do an example showing how this works for enriching uranium and how much one stage will do to change the abundance ratio. Thanks for listening, and I'll see you all next time. Bye-bye.